the server event for Engineering and Life, but I'm going to give it another minute or two to let people trickle in. And then, Dr. Yin, I'll give an introduction for you, and you can just take it away from there.
Okay, sounds great. Thank you.
All right. Thank you, everyone, for joining us for another Engineering and Life presentation. These presentations are opportunities for working engineers to talk about their careers or their career paths. We hope that you will continue to join us for future presentations and that you enjoy this one. If you find the information here today to be useful or just entertaining, we would very much appreciate it if you told your friends about us. This presentation is being recorded, and a link will be shared in our announcements channel when we post a video online. Today's speaker is Dr. Yen. He will be sharing some of his background as a civil engineer and how he got into working with the nuclear industry. If you have any questions at any time, you can type them into the thread found in the large meeting room chat room, and we'll open up a Q&A session at the end of the presentation. Everyone is welcome to share their story. If you think you might like to give a presentation yourself, you can message me or anyone else with the event coordinator role, such as Panda. With all that said, Dr. Yen, could you please take it away?
Yes, thank you for the introduction. As stated, my Discord name is Yen, and I have a PhD in civil engineering, and I'd like to sort of give a look into my path and how I chose the direction that I did, going from um, starting university and starting in civil engineering, and as the title says, going into the nuclear industry, and that was um, sort of developed from my PhD path. So I'll sort of give that description in a little bit here. So first, I'll start with the agenda. And I'll just give a brief introduction to my background, and then I'll start with my career path, sort of going through university all the way up until where I am now. I'll talk about my undergraduate studies and what I did for my bachelor's and master's, and any extracurriculars and some projects that I did along the way as well that were kind of interesting to me and kind of helped me on my journey here. Then I'll talk about my graduate studies, specifically my PhD studies. And then we'll move to project highlights. So this will just cover a bunch of projects that I did in university that I think were, very interesting and, very helpful. And then I'll give a brief, it says here, nuclear reactor analysis. It's a very, very high level description on the work that I did with my PhD, and if there's interest for a more technical discussion on that, perhaps we can arrange something like that in the future. Um, I'd be more than happy to kind of go through it more, but it's a very technical talk, so I don't really want to put too much of that into this presentation here. And then finally, I'll just talk about some of the stuff that I do currently at work. Again, at a sort of a very high level description level. And yeah, and then of course we'll take questions and see where that goes. So first, for the introduction here. So let's talk about my education and work introduction. So I went to the Illinois Institute of Technology, which is a university in Chicago. It's very near the downtown area, and so you can see there's a little picture on the right side here that kind of shows a very detailed and probably edited or very you know someone who's very good at photography took this photo, I guess, of the campus basically for Illinois Institute of Technology. You can see the Chicago skyline in the background there, which is really nice. Um, and then, yeah, just a, you know, sort of a nice snapshot of the campus. It's a pretty small campus, kind of all pretty well contained within the Chicago area. And on the right-hand side, I don't know if you can see my cursor here, but on the right-hand side, you see these two kind of like tube structures. So the top one here is an actual tube that's built around the CTA track, which runs kind of in the middle of the campus there. And the CTA track runs on top of a building. Rather, they put the building under the track. And so they put this tube here that kind of limits the vibration effects from the track onto the building there, which is kind of interesting. And the smaller, or not the smaller, the one underneath it there is a residence building that's actually modeled to sort of play on the that same sort of aesthetic of the tube structure, which is kind of interesting. But anyway, back to the main part of the presentation here. So I have I got all three of my degrees at this same university here. So I have a Bachelor of Science in Civil Engineering, Master of Engineering, sometimes called a Professional Master's. It's non-thesis based in Structural Engineering. And then I got my doctorate in Civil Engineering. And currently, I work as a mechanical engineer, and I put little question marks, how does that work? How does a civil become a mechanical engineer? And I work at the Argonne National Laboratory, which is kind of pictured with a nice bird's eye view on the bottom left here. You can kind of see this is pretty well, I believe, the whole campus. It's pretty large. It covers a wide area with a few of the iconic buildings. I don't know if you can kind of see on the bottom right here. The circular is the APS, which they do a lot of really great research there. I have nothing to do with that building, but it's a very nice place to work, and I'll talk a little bit about that. And if people have questions, I can discuss that a bit more. But just as a disclaimer, this is not this presentation is not like it's my personal presentation, and it has nothing to do with any of the what Argonne might want to say about themselves or anything. So it's mostly a presentation that's not focused on Argonne specifically. So I want to talk about my career path, which is the education and work timeline here. I call it career path because as we all kind of know, university itself is for the development of your career, and it's not necessarily for everybody, but nonetheless, this is where your career basically starts when you start university. And so I started in 2011. You can see on the left side, 2011. I started right after high school, and I went straight to university. And I went in for civil engineering to get my bachelor's degree, and I was kind of back and forth on a couple different options and what I wanted to do, and it was mostly between civil and mechanical, and kind of not quite sure at that time which one I wanted to go for. So I just kind of picked one, and I was just like mechanical. A lot of times they sort of advertise their robotics this and a lot of other things that I really didn't have much knowledge of. And I guess at the time I was slightly interested, but the idea of civil and the fact that it's usually associated with large infrastructure projects. Most people know like bridges and buildings and roadways, and that was sort of the thing that kind of drew me in a little bit more than just the standard what you think of mechanical. And I know mechanical itself is very broad as well, but the just the idea that there's so many different things in civil, and I just I figured, okay, it's a very general field. That's where I'll start, and then you can specialize later. And so what I did, I'm going through university, and in 2014 I applied for and was accepted into what my university calls the coterminal program. And the coterminal program was um, you basically can apply for a graduate level degree while still being an undergraduate level student. And it just extends your university by 1 year, usually. So instead of doing depending on your degree, instead of doing the classic 4 years, you would do 5 years. So it's like 4 plus 1. And then you would graduate with both your bachelor's and your master's degree in whichever program you apply for. And so I did this for structural engineering because that's the area that I decided that I wanted to specialize. And then the way it kind of works, it works differently in different universities and institutions, but a lot of the upper level elective classes are shared across both the bachelor's and the master's program, and so it double counts a number of credits, and that's why you're able to do it in 1 year instead of 2 years. And then, of course, it also eliminates the research focus. So it's mostly for people who want sort of that master's level education so that they can go and get a job that requires a master's degree without having to do research, which is a lot of time what structural engineering requires. They'll usually require a master's. And then as I'm going through studying, I decided that I wanted to apply for a PhD. And so that was kind of the unique part of my journey here is I got to know one of the professors who taught a number of the structural engineering courses. So I had him a lot for undergraduate and then for the grad courses for my coterminal program. And he was just like, "Oh, well, I have this idea for a project, would you be interested?" And you'd be applying for a fellowship, which I'll discuss later. And so that's what pays for the research. And I figured, well, this is a good opportunity. It's a professor that I've had for multiple courses. I kind of liked him, and figured, okay, well, yeah, that's I'd like to do this, and why not? So I applied for and got into the PhD program after I graduated in 2016. Well, I applied before I graduated, and then after I graduated, I started. And so in May, I graduated, and in the summer, I started sort of right away doing this PhD work. So not even waiting until the fall semester, which is pretty standard for PhD. You're kind of like pretty much always working. um, and the project had to do with I'll discuss a little bit later, but it has to do with structural analysis for nuclear reactor cores. And so that's where the nuclear aspect comes into this, is that it's still a structural mechanical aspect, but it's applied to nuclear industry and nuclear research. And from there, as one of the terms of my fellowship, I was supposed to work at a national lab for an internship for a summer. I believe it was 10 weeks or 8 or 10 weeks or something like that. And so I did my internship with Argonne National Lab in the summer of 2018. And that's kind of where my, I guess you'd say, the relationship with Argonne actually happened. Um, and then in 2019, I had the classic thesis defense. In PhD, you write your thesis, and then you have to present it in front of a committee, and your friends and family and whoever else wants to come and join. Most of the time, they're pretty open as long as everyone is non-intrusive and not interrupting anything. Um, and so then right after that, I basically started working at Argonne as an Argonne associate, which is a temporary position that you can work for like I think it's up to 3 years maybe in this position, but it's not a permanent employment opportunity. And so I was working with them doing that, and then I graduated um, in August technically. So it's there was a little bit of a time lag there, and then just last year in April they hired me for a full-time position, and so I've been working there now for about a year and a half, maybe a little bit more than that at this point. And it's been absolutely wonderful. So that's the basic. That's the basic timeline there. So I'm just going to kind of go into a little bit more detail about some of my undergraduate studies. So as I mentioned, I started my bachelor's degree in 2011, and I just put some relevant courses here. These are some of the courses that kind of stuck out to me as I was doing my studies, and like the ones that are usually lay the foundation for most of the work. You see here, the first one I put is MATLAB. I know a lot of people might have issues with MATLAB. It's is it a real coding language? Is it not? I assure you it is. But I know a lot of people don't necessarily like it, or they just have issues. I actually had a course learning MATLAB, which was great. It taught me a lot of the basics. It also taught me a lot of the very, very basics of like computer science and learning even how to code. So it wasn't just focused on the MATLAB portion, which was great. I use MATLAB almost every day at work. So, and then of course there's the standard civil, mechanical, structural courses: statics, mechanics of materials, and then for structural analysis, and steel and concrete design. And so these were all of the courses that kind of they lay the foundation for everything that I do now in work. Almost everything I did with my PhD, even except for the concrete. I don't really do much with concrete anymore. Um, and yeah, so I mean, these are the fundamental courses. Some of the other things that I did while I was doing in my undergraduate studies, we everyone at Illinois Tech, as they like to call it, has to do this, or I think 2 semesters of an interprofessional project. They call it iPro. I'm not sure if they've changed the name yet. I know at one point they were doing the sort of I think a contest for trying to rename it because they didn't like the name anymore, but I haven't heard anything about that. And basically what you do is you sign up for, whichever project you want to do. They just kind of have a list of all the projects, and you sign up for which ones you think are interesting. I signed up for what they called the STEM education cluster. So they had a number of different projects that you can sign up for, and you work with an interdisciplinary team on a specific project that is either well defined or maybe not so well defined. And maybe the first semester of the project you're working on defining what the project should be, and then future semesters can iterate on that and take the design further, or change it even. Ours was a second semester project. We were kind of um, working on something. I'll discuss it a little bit later. It's actually one of the project highlights that I want to talk about, but it's very, I'd say, very important class project that we had to do, because you're working on a team of people who aren't necessarily the same field. I know in mine we did have 3 civil engineers on my project, but I think we had about 10 people or so, and we had people in all sorts of different fields. I'm not sure if we had someone from architecture, but usually, you have architecture students, other types of engineers, some business majors. So it's just kind of like a almost like a random assortment of people, and you get to kind of work with a bunch of people who have different. They look at problems differently, and you get to work with other people, which is very important because in work, obviously, you work with a bunch of your colleagues. All have potentially different degrees, especially if you're doing engineering. You're working on projects. You have electrical engineers, civil engineers, mechanical engineers, all working together to um, you know to finish whatever sort of project you're working on. And so it's a nice way to kind of introduce a student to that sort of environment with a class project like this. Um, yeah, so then after that, I joined the coterminal program for my master's degree in 2014, and I graduated together with my bachelor's and master's with one extra year of schooling. Um, and I'd say some of the relevant courses that I took for my master's, um, things like bridge engineering and finite element method. Now, I don't actually do very much with bridges now, but I took two courses actually in bridge engineering, and it was very, very interesting to learn about this topic. And then one of the other very important is finite element method. And so I know a lot of people might not know what this course actually is, but it's a very, very important course for civil engineers, structural specifically, and mechanical engineering, because it's applied for a large number of analysis type, projects that you do at work, and um, a lot of the software that you might not even really know what finite element method is, but the software itself might utilize it to actually solve the problem for you. So it was a very important course that I took. They actually talked about the process for how like what the finite element method is, and and how it's actually applied. And then I took a couple courses where it's you know here's how the software actually works, doing this sort of method. So and it's very important, because a lot of the work that I do now uses software that has this, um, when you're doing frame analysis structures, um, actually, nuclear reactor analysis, the structural part of it, we're using finite element method for that and everything too. So, um, yeah, just wanted to talk, briefly about that. Um, so I'm just going to move, quickly to the grad studies here. So I started my grad school for the PhD. So, um, yeah, just to note, I think I mentioned this before, but the with the coterminal program that I did, so even though I was working on like undergraduate and graduate courses, and then eventually just kind of working on only grad courses, I was still technically considered an undergraduate student. So I wasn't even really a grad student at that point. Um, so I didn't really start grad school until 2016. And so the PhD that I worked on was funded by the Department of Energy through a fellowship program. I don't have all of the letters here. There's it was an integrated university program fellowship, which the Department of Energy funds, and so they have a number of these. Depending on which university you go to, they might have some sort of an agreement with them to actually fund this sort of fellowship. Um, and the way that a fellowship works is you apply with a proposal for a project, and then they will go through all of the applications, and they'll, approve or not approve whichever ones that, they think are interesting, and which ones follow what sort of, parameters and guidelines they set for the type of work that they want done. And then you get to work on that basically as a research assistant, funded through a fellowship. Now, a lot of other universities, they'll have um, departments or lab programs, or however they term them, which has its own internal funding that can fund a lot of studies. Usually at smaller universities and smaller departments like the one that I was working with, they don't really have a lot of funding for stuff like that. So this fellowship basically funded my entire PhD, which was very helpful. Um, just to talk about what the research that I did, was called uncertainty analysis for nuclear reactor core bowing, and the core bowing aspect is just the type of deformation and analysis. So I can talk about it a little bit more, but the bowed shape is just the shape that the internal components take when they undergo this thermal expansion. And uncertainty analysis is basically when you take a look at the deterministic system, which is all the values, the parameters for things, and you try to run the analysis. And the uncertainty analysis is for when you claim that you don't know what those numbers are, but you have some sort of a distribution for what the numbers should follow. And then you can work the analysis doing something like that. I talk about it very briefly at the end here, just to kind of give an overview of what that is. Again, if people are interested and we want a more technical discussion, I'd be more than happy to organize something like that. And I can go a little bit more in detail. I have an entire presentation already made for it, so that would be my my thesis defense. So, um, and then just to talk a little bit about some of the relevant courses for this part of my academic career. So the first is continuum mechanics. A lot of people might not know what that is. Normally, when we're talking about like if you took statics or even a lot of times in dynamics, a lot of times you're working with like point loads and like point bodies, and you kind of sort of assume that things act at like specific locations, and continuum mechanics just kind of is an expansion, a very high level version of that, where it's like we're going to assume that the body is a continuum of space, and you kind of work the analysis like that. And it's one of the most difficult courses I've ever taken in my entire life. So um, it's very tough, very math heavy. So just to kind of talk about that. And then I took some sort of random classes. One of them was called Homeland Security Concerns in Structural Engineering, which is a very interesting course, mostly project based, and that's another one of my project highlights that I'll talk about. And it's basically kind of looking at um, how structures might be viewed in a security stance where they can be vulnerable to attacks, like terrorism attacks or something like that. Um, and kind of looking and seeing, okay, well, how can we either mitigate these? How can we design for something like this to happen, like a blast load from an explosion or impact load from getting hit by a car or something like that? Or even in the more general sense of not necessarily the structural analysis, but like, how can we, design the pathway through, a specific area to allow for, better access for emergency personnel, better exits for, people who are, might need to evacuate an area, something like that. Um, and so one of the topics I'm going to talk about is the project that my group did that we actually published a paper for. Um, and then some of the other courses, I took a seismic design course, which is very interesting. It's for earthquake engineering. And then this building envelope rehabilitation, which is taking a look at a structure and looking at the outside of the structure and trying to find out, okay, well, what are some of the issues that are happening with this? The envelope of the building is sort of the outside of the building, and like looking at cracks and moisture leakage into the building and inspections and things like that. And one of the project highlights that I'm going to talk about is our project for that course as well. And then another course I took was this statistical tools for engineers. Is another very important course, especially if you're going into research, but even if you're not necessarily doing heavy research. Needing to know basic statistical tools and being able to analyze data for different types of analysis or something like that is very important, I think, for a lot of engineers, and it's one of the things that is not necessarily focused on, I think, in a lot of programs or universities, depending on the field, I guess, that you go into. So one of the bullet points I have here is this Homeland Security concerns. We did a project. It was basically risk assessment of vehicle threats to pedestrians in open spaces and open gatherings outside. Um, Especially around Chicago area, there's a lot of outside festivals that happen, and people are congregating, and they can be at risk for vehicular attack. Um, and then this building envelope rehabilitation focused on doing a critical examination of a building facade for one of the buildings on IIT's campus, which was Alumni Memorial Hall. I'll show some pictures of that. It's pretty shocking. um, Moving on to some of the extracurriculars that I did while I was doing my undergraduate, mostly graduate, and that was kind of a mistake on my part, is not getting as involved as I should have during my undergraduate studies. I know a lot of people, they are, and that's really great, and you should be, finding, the engineering, clubs and organizations, and the projects that they work on, and getting involved in that is is very, very important because it kind of gets you out there working on things and potentially getting, um, you know, sort of this, connection to other engineers and in industry as well. But some of the stuff that I worked on, obviously, as a PhD student, I was working as a research assistant, which basically means that you work for um, sort of your program. You'll have a PI, which is the principal investigator for a specific, project or lab or something like that, and you kind of work doing, research, which kind of assists in their expertise. Mine, since it was funded through a fellowship, I pretty much worked mostly on my own research for my PhD, and then doing some, random things around the department. I joined SEAOI, which is in the Illinois chapter for the Structural Engineering Association, which is our student group. I also joined Chi Epsilon, which a lot of people don't know about, which is a civil engineering specific honor society. Um, so it's sort of, I'm sure most people have heard of Tau Beta Pi. It's on the same, idea as that, but specifically for civil engineering and not just general engineering. I also helped organize some graduate student seminars when I was doing my PhD. So we just had, um, I don't think it was every month, maybe every other month or so, we would have one of the grad students come in and kind of give a presentation, about 30 minutes or so, talking about some work that they were doing or, some research that they had performed, and just to kind of, you know, get together and everyone can kind of learn what everyone else is working on, because that's another thing you don't really get so much when you're doing, graduate students. A lot of times they don't really talk that much with each other about the work that they're doing. I mean, if you're working in an office with someone, you might, talk with them and kind of, have some sort of a rapport, or, like have lunch or whatever, but you might not necessarily know what someone in a different office is working on, or if you're not really, talking with them as much. So this was a great way to sort of um, get together, have a sit down presentation and then discussion afterwards. And of course, on my side, it was great to kind of help organize these seminars. So I kind of get a little bit of, experience helping to organize presentations and things like that. Um, I also helped co-organize a scholarship award luncheon and lecture. So we had a specific scholarship in my university that they would give to some students, and with my advisor, we kind of co-organized the luncheon for it. I don't know, I think we had maybe like 100 or so people there. We brought in engineer William Baker, who actually helped work on the Burj Khalifa. So we had him come in and he gave a talk about that and other sorts of engineering, projects and stuff that he had worked on. And then finally, I also worked as a teaching assistant. Um, a lot of universities might require this for grad students doing PhD. You have to work some semesters doing teaching assistants. Um, it's not actually required in my case, especially because I had a research fellowship. Teaching was not necessarily required for that. But I enjoyed doing it. I helped with some of the structural analysis courses. I taught some lab classes. Specifically, if anyone has heard of, it's called SAP 2000. I think there's another popular program called SAP, completely different. So just in case, you can actually look it up. It's SAP 2000. Um, and then I also helped with the building envelope rehabilitation class that I took that. I believe I took that my first semester as a PhD student, and then I think my second to last semester I was the TA for the course, which was nice, considering I had actually taken the course. Sometimes sometimes you'll have a TA who's not actually taken the course, but they're familiar enough with the material, and it can be a little bit daunting with the way that they help with the course. But um, so now I kind of want to talk a little bit about some of the projects that I worked on as a student. So these are all student projects; they're class projects mostly, and they're the reason I want to highlight them. I'll talk about for each one specifically, but they kind of give a very very important look into some of the things that I learned when I was a structural engineering student, um, and like some of the stuff that you would eventually have to work on uh, as an engineer in the workforce. So the first one I want to talk about is the iPro project that we worked on, and it was with the collaboration with Adler Planetarium, um, and so that's the planetarium in Chicago. And what we were kind of working on with them was a redesign of their meteorite exhibit, which I have some pictures of on the slide here. You can kind of see on the bottom. It's very simplistic. It's got some good information, but it's not really that interactive, especially for younger kids that kind of look at it and say, "Well, what is this?" It's not very descriptive. Um, Although they do have an actual meteorite kind of sitting there, which is nice. Um, and again, the interprofessional project. This is an interdisciplinary team. And yeah, so this was the second semester that they did this specific project. And the first semester, um, they kind of had like a no, what's the word I'm looking for here? Like the sky's the limit approach. They're just, we'll just kind of come up with, two or three of the best ideas that we can. They weren't really thinking about the space requirements. It was just, let's just run with it and kind of, go as far as we can. And then second semester, we kind of looked at it and said, okay, well, let's actually put some physical bounds on it. This is the space that we have to work with. And while we didn't necessarily think of like the costs associated, we did think about, well, let's not do something that, is completely infeasible, based on the cost. Um, yeah, uh, so this is kind of what we came up with. I know it looks a little bit funny. These were actually done in MS Paint. I did not do these myself. But we came up with a couple ideas, and our most popular idea that actually started gaining more traction was we came up with this as a secondary idea, and it actually overtook our first idea. And it was a three-station exhibit mock-up for what we called Marty the Meteor. And it was sort of a slightly or a more interactive experience, I think, and especially geared towards younger kids to kind of get more information on what meteors are, how do meteorites form, and what actually happens to them as they come through the atmosphere. So, like the first one was just to kind of give information on what meteors are and where they come from. The second would be a different part of the exhibit that kind of demonstrates the physical phenomena as they're coming through the atmosphere and the with slight resistance from the atmosphere and friction and stuff like that. And then the third one is supposed to be more of like a, well, let's kind of shoot a meteor into the dirt, sort of like the initial exhibit that they have, but put a little bit more flair on it and kind of give it a little bit more of an appealing look. And so we kind of had a very simplistic mock-up. We actually kind of built some exhibits, like stations, and gave a presentation. The way that iPro works is at the end of the semester, they have what they call iPro Day, and they go in one of the buildings that has all the space, and they set up all of the projects with your posters and any sort of like in our case, our exhibit, and any sort of other materials you have to sort of illustrate your project. And so we actually kind of made these out of cardboard and poster boards and stuff, and kind of set them up and kind of walked everyone through what our exhibit was going to potentially look like. I'm not sure that they actually went and built this. I hope they actually had another semester where they looked at it in a little bit more detail and kept going with it. But I'm not entirely sure about the any sort of progress that might have been made on this. This was a few years ago now, so. Um, so one of the other projects that I worked on, which is another class project for our concrete design course, and this was to design a concrete parking garage. And the way that the professor kind of proposed this to us, and he gave this to us at the beginning of the semester before we'd really learned anything. Although this was our second concrete design course, so we had some knowledge, but The idea was he just kind of gave us the prompt, which was, all right, here's a plot of land, here's how large it is, and what you need to do is design a 2-story parking structure. So the ground level and then the roof level, and the roof level would be available for parking use as well. And there were teams of 3 or 4. Ours was a team of 4 because of the class was not divisible by 3, so one group had more people, and that was ours. And the way that we kind of had to approach this, I kind of laid out the steps here. We kind of had to, develop a schematic for the garage, including an elevator location. So there had to be at least one elevator located somewhere in the building. Usually, in the case of buildings made of concrete, you would have some sort of a core in the center or somewhere around the outside edge, and that's kind of the best place to put one. I won't necessarily get into why, but there are very specific reasons for that. And then from there, we have to kind of identify the potential loading on the structure, in this case, using the Chicago Building Code. Illinois Institute of Technology is in Chicago, but even places outside of Chicago, a lot of times they don't have their own building codes. They'll use the Chicago Building Code if they're anywhere around Chicago, or the International Building Code. And this is where you kind of get the loads on the structure, like, okay, well, how much do we assume, the people and the cars are going to weigh, and then any sort of other effects like, potentially rain or snow, because it's affecting, the outside top level. And then from there, we have to go and actually, do the design, which was designing, the foundation, which holds the structure up, designing the beams, the columns, and then the roof slab, which is going to hold, the cars on the roof. And then also, so we have to do these designs when we have to, provide, detailed calculations and then detailed drawings of all of the standard components that we have. Now, this design that we ended up doing is not necessarily, completely typical. A lot of times, parking garages will use pre-stressed concrete, and this was not a pre-stressed concrete course. So, I mean, we just had simple reinforced concrete, which might not mean too much to everyone here, but that's that's the way that we kind of did that. So, some of the examples of what the drawings might look like. These are the actual drawings from our project. So you just we had to show the layout of the building, which is showing all the main beams, which are in blue, and then the secondary beams in red. Each of these squares is a column location, so we actually did have quite a few columns. A lot of times, if you use pre-stressed concrete, you can space them out a bit more than that. So ours is not necessarily the most efficient design, but and then the elevator located here, and just show the dimensions and the callouts for specific things like that. This is typically what you'd have to do in an engineering project like this. And then we have the detailed cross sections for some of the things like the beam in the middle here, which shows the beam size and the reinforcement location and how much. And then on the far right here at the top, you have the column cross section, and then on the bottom you have the elevation view for the foundation. So it shows the column connecting to the foundation at the bottom, and then the ground level with the soil on top. Or anything else on top. I mean, depending on where you put the foundations, they'll be below the ground level. So you'll have things on top of the Um, let's see here. Yeah. So yeah, this is it was a great project, I think, in my opinion, because we all had to kind of work together on it, and each person ended up doing a specific type of design. So one of the guys in our group was the one who did all of the drawings in this case. He did all of our detailed drawings. We have a few more that I didn't put here. And then one of the other guys in the group did the beam design, and then I did the column design, and then someone else did the foundation design. And so that was kind of had to work together to kind of figure out, okay, well, we need to know all of these different components because we need to know the size of the columns to do the beam design, because if you have the beam sitting on or near the column, the like the width of the column and the beam kind of have to match. Otherwise, you're going to have some weird detailing in order to connect them, and it's not going to work very well. So it was a very, very good project to sort of, get a group of people together, have regular meetings on how to do the design, what do we want to do, and then come up with something together. And then, end up running with it and doing the individual components and then coming together and putting it all together. So now I'm going to transition to some of the projects that I worked on in my grad studies. The first one was this risk assessment vehicles to social gatherings. As I said, a lot of times in Chicago, we'll have these, pre-COVID, of course, we have a lot of outdoor gatherings of some kind, music festivals, Taste of Chicago, things like that. And around the time that I was taking this course, there were actually a lot of incidents that were happening, not necessarily in the United States. A lot of times they were, overseas in Europe, or I think most of our case studies were in Europe, but I think a couple of them were actually in the U.S. And we kind of took a look at this and said, well, maybe we should kind of bring this to people's attention, so that we can come up with a more planned strategy for how we can assess these risks for vehicles. And so the main idea of the project was to analyze the risk posed by vehicles to pedestrians in crowded gatherings. And part of the project then was to kind of determine the types of vulnerabilities that exist and how we can mitigate these with specific barriers. Where should we place them? Should they be permanent or temporary, depending on if it's a very high traffic pedestrian area where there's always people around, or if it's just for a specific event that's happening. One of our examples was in 2016. There was a Christmas market in Berlin that was attacked by a hijacked truck. On the left, you can kind of see the path that was taken in red, which is coming right off of a roadway here. And there was a nice opening where the truck could just get right into the market and just kind of wreak havoc. And then you can see at some point it did actually come out of the market. And here's a picture of what it kind of looks like with this nice big open area that a large truck. Coincidentally, the picture that we have here has a truck right next to the opening, and there was really no barrier here, temporary or permanent. In this case, potentially temporary would be the best to stop a vehicle from getting in. Of course, one of the major things that we have to think about in this incident, or in situations like this, is a lot of times there aren't permanent barriers around roadways like this, and the very specific reason, at least in the United States, is to protect the drivers, because if there's a permanent sort of barrier there, and some accident happens, or you lose control of your car and you hit it, well, that could potentially kill you, as opposed to maybe stopping the vehicle and not injuring you as much. And so that's one of the things that we had to think about while we're doing this project is, what can we do to protect the people, on the streets, but then also protect, not and not injure people in their cars when they're not actually trying to, do anything, unsavory or something like that. We had a lot more examples, and we actually published a paper with our risk assessment and some of the potential, solutions that we had, or things that engineers and designers can think about when they're doing this event planning sort of thing. So yeah, here, like I said, we published a paper, and then actually we gave our presentation to a number of different entities and organizations. I say interested groups. We gave a presentation actually at Rush Medical Center for one of the guys who's in charge of sort of security, I guess, there, which is located in Chicago. We also gave a presentation at the Chicago Police Department, Unit 116, which is near IIT. We had our professor had a working relationship with one of the officers there, and he actually came to our class and gave a presentation, and kind of like, talk to each of one of us about our potential projects and how we can go about doing them. And we actually gave a presentation at their department unit with a bunch of their officers who are, they're in charge of sort of, I'm not sure if it's necessarily inspection, but going through some of these events and, trying to label out the risks and how they can be, mitigated and stuff like that. Um, we also gave a presentation at FEMA Region 5, which is in Chicago as well, one of the federal buildings. Um, one of the officers, or I'm not quite sure how they're classified there, but one of the guys who worked there also gave a presentation at our class. Our professor knew quite a few people, and so we got together with him and gave a presentation to his group over there. Um, and then what else? Oh, also our in Chicago, the Office of Emergency Management, which is also quite near IIT as well. It's a little ways away, but not too far. And so we gave a presentation to them as well in their group, and it was very well received by everyone. We got a lot of good feedback as well, on potentially what we can change with it, or because I think a lot of these presentations happened before we published our paper, so that kind of helped us with some of the gaps that we had. And I think this is one of the last ones I want to talk about, which is the critical examination for Alumni Memorial Hall. So this class that we had was talking about the building envelope. So we're looking at the outside envelope of the building, which is the barrier to the inside and the outside, so that the walls, the doors, the windows, things like that, and kind of noting any issues that are happening, and then how can we potentially fix them. So Alumni Memorial Hall is one of the it's actually a famous building on campus, which is hard to believe considering the state that it's in. Um, it's one of the academic buildings. It's actually, interestingly enough, is the department location for the civil engineering department. And in my opinion, at the time, was one of the worst conditioned buildings that we had. It was designed by Mies van der Rohe in 1945. That's where it kind of gets its popularity. And Mies van der Rohe, very famous architect in Chicago, designed another building, Crown Hall on campus. It's a very famous building. Has the beams on the outside. Just kind of leave that there. And then, so the purpose of this critical examination, which normally you wouldn't do on a building of this size, a critical examination would be for a high rise or bigger, but we don't really have very many high rises or the ability to inspect a high rise. Yeah, so we had to inspect the exterior of the building and report on any damaged features, and then suggest some immediate and then long-term repair issues. So anything that we think is needs to be fixed right now, and how should it happen, and then long-term repair and maintenance for some of the issues that aren't necessarily critical, but they do need to be fixed. And so you can kind of see, this is a picture on the right-hand side of the building itself. You can kind of immediately see all of the rust on this exposed steel. So that was, of course, one of the major issues that we had with this critical examination, but there's a lot more, and I'm going to get into that actually very quickly. So I got a couple slides here which show some pictures. This right here is a window frame, and you can kind of see that there is an opening that you can see directly inside the building. And so this window frame is not actually doing what it's supposed to be doing, which is blocking the air coming into the building. So even if your window is closed, your window is actually open. You can kind of see all of the sealant is peeling away from the building here. And this isn't the same location, but at one point we actually did take a picture with a tape measure here, and you can see that it's at least 1/4 of an inch thick, this opening. So that's not very good. There were numerous locations where this was actually a feature. Then, of course, one of the other things that we need to look at is cracks in the facade as well. The facade, just the outside exterior wall building. A lot of cracked locations in the concrete, or not the concrete, I should say, the brick and mortar. You can see here, this is the outside corner of the building, and it's cracked, and you can see that it was sealed at one point, but it's just continuing to crack and pull away. This is one of the joints on the building. You can see that there's a large opening here. And then, of course, we have a lot of vertical and even inclined cracks running throughout the building. So we had to go through and report on all of these. And this very short look at some of this, but a lot of the fixes that we did talk about were immediately the windows, the window fixtures, all of the the things like that. And I mean, of course, this was a class project, so I don't know how much they actually did with that knowledge. As far as I know, they didn't do too much until they actually did replace one of the windows. But I'm not sure. Yeah, I don't have a picture of it. One of the windows was actually broken, and so they had a cardboard kind of, or not a cardboard, a plywood covering for it. And yeah, so it was not a very good. It's an old building, so I mean, there's a lot of work that could be done on it. But yeah, so that's kind of the very brief discussion on this. So the last main topic that I want to talk about is this nuclear reactor analysis, I say, and that's the main topic for what my PhD was geared towards. So I'm going to give a very brief introduction to nuclear energy. If there are any nuclear engineers in the listening to this presentation, I'm sure they will cringe at my explanation. This is and I know it's a very generalized, and there's not a lot of detail in this introduction, but yeah, so a nuclear power plant, I'm sure a lot of people know that they exist, of course, but it's a thermal power station that converts heat energy into electric power, and it uses this nuclear reactor as the heat source for it. And here is a very simplified schematic of how that actually happens. And so, of course, you have the containment structure, you have the reactor inside of it, and then you have steam generators and turbines that generate this electricity, and then the cooling towers, and then the coolant water goes through and cools down the steam back into water, and it has this sort of loop here. There are a bunch of different types of reactors, and so it's not always the case. And the type of reactor that I was focused on is what we call sodium-cooled fast reactors, and so this is a generalized schematic of what that might look like. And all of my research happens on just this tiny reactor part, not the rest of it. So there's a lot of work that goes into kind of doing risk assessment analysis and other types of analysis for all these other components, and that's out of the scope of my work and, of course, this presentation. Another kind of brief introduction part is that the reactivity is what measures the state of a reactor's power generation. A lot of times, you'll hear, something's, radioactive or something's reactive or something like that, and that's kind of where this comes from. And the important part is the relative change in the reactivity level, and it's very sensitive to the location of where the uranium fuel is in the reactor. By what I mean by location, I don't think I have a very good picture of it. Each of these little rods, so these are control rods, but inside of the reactor there are also other types of assemblies that have fuel in them, and they'll be mostly located near the middle of the reactor portion, and they can move in and out depending on how deformation happens within the reactor. And when it moves in a sodium-cooled fast reactor, even small changes in that location can drastically affect the reactivity. And so that was the focus of my PhD, was to kind of look at this in an uncertainty analysis aspect. And so a very kind of a nice description is that the location of the fuel relative to where the neutrons are generated in the reactor affects the time it takes for fission to take place. And of course, neutrons move very, very quickly. But when you have larger gaps, things can kind of move in between those gaps and they kind of get lost. And so it makes things take a little bit longer and the reactivity can change. And some of the changes are based on fuel density. So the density of the fuel can actually change bowing deformation, so that's kind of the shape that these assemblies will take. Buckling of these. Buckling, depending on your knowledge of structural analysis, buckling is a very sudden failure and it can drastically affect any sort of structure. And then high stress deformations, and that's just when you have high stress, you have inelastic stress. It can permanently deform the structure in different ways. And so a lot of these things are taken into account in this sort of analysis. Now, where my research comes in is the fuel assembly and core restraint system. And so a nuclear reactor consists of an array of hexagonal ducted structures. So this in the middle here is just a very simplified drawing of one of these assembly ducts. And a duct, in this case, the cross section is a hexagon. You can see it on the left here. And they're thin-walled steel structures, and they kind of sit vertically in the reactor. And they can, depending on the way that they deform, the fuel would be located in a very specific portion in the axial direction. And as it moves in and out, it changes the location. And so on the left is just kind of like a bird's eye view cross section of a full reactor. And it has a number of these different types of assemblies inside. So you'll have like an inner core region, which is this yellow color, an outer core region, reflectors and shielding, and all types of different assemblies, and then the control rods, which kind of control the shutdown and startup. And they sit in the reactor. Depending on the type of core restraint system you have these rings on the outside, and they're extremely rigid, and they control the total amount of outward deformation that you have with these assemblies. And the point is to get it to a point where you can actually estimate the location of each of these assemblies so that you know where they are at any point in time. It's a very complicated analysis, and it very significant role in the effects of the reactivity changes. And so sort of the methodology for this uncertainty analysis that I was considering, if you kind of take an elevation view on the right-hand side, each of these is one of those ducts. And they kind of, if you look in like any line of ducts that you have, you'll have different locations on there that they're allowed to contact. These are called load pads. I have I have a couple different abbreviations here that I didn't really explain, but these are just different load pads that contact. When this assembly can deform like outward or inward, it'll contact at these locations here. And you can see that there's a lot of different geometric parameters that will control this. There are different gaps here at the load pads. There's gaps down here at the bottom with this nozzle. There's gaps on these restraint rings, which is on this ring on the previous slide here. That's kind of this cross section. And so there's different parameters that affect the performance of this system, which of course the material properties, what kind of steel are we working with, the gaps between everything, the nozzle clearances, these restraint ring clearances, and the lengths, even the length of the assembly, of course. And so the basis of uncertainty analysis is we're going to kind of look at a real system. And when you manufacture something, these real dimensions that you have aren't exact. And they have what we call uncertainties exist in the as-built system. And when you kind of look at what we call deterministic model, where you determine what every single dimension is or parameter, and maybe you just adjust one of them for a design purpose, you still set the value and run the analysis. And so this uncertainty analysis, we say, well, we don't know what the width of this actually is, but we have a range of what the values are supposed to be. And we might say it follows maybe like a normal distribution where the average value is the most prevalent value, and so you can kind of use that as a method to sample some points and get some values. But considering these uncertainties is extremely important to quantifying this reliability of the reactor system, because if you have a small change in something, depending on the analysis, can have a very large change in the output. And as I said before, very small change in this location of the fuel, which is somewhere around here in the axial, very small change in the location could drastically change the reactivity component. And so that was one of the things that I was looking at is, well, let's just take a distribution for some of these geometric values and run a bunch of different analyses and try to come up with a method for quantifying, what the differences are supposed to be. So this is a very, very simplified type of output that I was getting for some of my uncertainty. And so you'd say one of these vertical lines, or one of those vertical assemblies, can take this sort of a shape when it undergoes some sort of deformation, say. And a lot of this is due to contact, and so something's pushing it in one direction. And yeah, so you have this shape, say, in the elevation view, and by just varying a couple of the parameters, or in this case just varying one of the parameters, you get sort of this deflection curve. So the line is the initial deflection, and these sort of bands on the outside are the variations in the position at that point. So what we're saying is that this actually has a larger variation in the shape that it can take based on varying some of the parameters. And so if I go back a couple slides, the reason that it affects it that much is, well, if you have a large reactor core like this that has over 300 components, when you vary all of them at the same time to a different degree, you're going to get a lot of difference in the displacement results. So that was just one of the aspects that I was looking at, looking at displacements and contact forces. And I don't want to get too much into the technical details because we can talk about that later. If there is interest, I can give another presentation and kind of go into that a little bit more. So that was sort of the way that I got into this nuclear field, doing this PhD. And I, at one point, got into contact with some of the people who work at Argonne National Lab, and some of them are, familiar with this kind of work in the deterministic sense. And that's sort of how my relationship with Argonne sort of, developed and grew from there. And that's why I was able to start working there when I did. And some of the work that I do is actually on this expertise that I developed during my PhD. So I'm just going to talk a little bit about some of the current work that I do, and I only have 2 slides here, so it's not that much. So I work in a division that provides engineering services to the lab and other non-lab customers, we call them. And so my position is not solely a research-based position, which is interesting given the fact that I have a PhD. But it was also, I think, good in the sense that, there's a wide variety of things that I can be working on, and not just, a small subset of, types of work. And so what, we provide an engineering service, kind of like a consulting firm or something like that. We provide, engineering design and analysis, based on what our customers, have as work. And so we have a broad range of engineering services that we actually do provide, CFD, computational fluid dynamics analysis, thermal analysis. Actually, someone is doing also a bit of magnetic analysis for, some projects. And we also do structural mechanical work, which is where my expertise falls. And then some of the other work that I do is also research-based work, which is based on the main area is called core radial expansion, which is this core restraint analysis. And that's based on the expertise that I have from my PhD thesis. And so a little bit more detail on some of the projects that I've personally worked on. And in a very broad sense, some standard frame design for a variety of applications. Some of the projects, one in particular, was working on repurposing an old structure for some new projects that they had. They had an engineering stand for something that held some sort of a machine on top of it, and they wanted to use it for a different purpose, like a different type of machine. And the idea was, well, here's the frames. Is this okay? And so I take the design, I put it into my engineering software. I model certain things. You have to make a couple assumptions based on the connections, and then just work through the analysis and kind of do the design check and say, okay, this is good. This will work. It's going to support the load with no problems. Some other things that we do, other divisions might have building upgrades or system upgrades to some of their resources, and we actually do provide services to do the engineering analysis and design for those upgrades as well. Usually, working with steel structures, but sometimes not. One of the projects I worked on was actually designing it's like a crane cart type structure to lift steel plates onto a wall. And it sounds very simplistic, but there were a lot of tight space constraints, and the size of the structure had to be a certain size to get it into the space and maneuver it around in a safe manner, and things like that. And also the plates were rather thick, so they weighed about 2,000 pounds. So um, some other work, I work on some composite frame analysis, composite material. So this we do as a solid analysis with ANSYS, if anyone's familiar with it. It's a high fidelity finite element software package. And then a lot of my work is also based on this assessment of this core radial expansion, um, based on my research expertise. And so we do a lot of assessment of some of the existing tools and how they can be applied to the work. And then also expansion of these tools to consider what we call multi-physics coupled analysis. And the multi-physics just meaning that we're trying to add in into the software to be able to calculate all of these different types of physics at the same time. So a lot of the thermal and fluids, the neutronics for nuclear reactors is very important, and then the structural feedback effects. So a lot of software does exist which calculates all of these individually. And so some of the work that we do is based on trying to combine them together so that they can take inputs from other software outputs, and do the analysis as a fully coupled simulation, which is very, very complicated to do. And so that's pretty much all I had here. I'd like to thank everyone for their attention during this presentation. And of course, I'll take any questions you have for me about my work, about my career path, education, anything like that. I'd be happy to take those questions and give you um, an answer from my point of view. So
Yeah, thank you very much for the presentation. We do have a few questions already lined up, but first I want to remind everyone that you can ask a question in the Engineering and Life Q&A thread that is under the large meeting room chat channel. Anything you have posted there, just say if you want to be unmuted to ask the question yourself. Otherwise, I'll read it out loud. One of these I know is from someone who unfortunately could not be here live for the presentation. They ask, Atran913 asks, what is the best recommendation that you can give to a new student that is starting in STEM?
Okay. I will. Let's see. I'm sorry. I will give I think what might be considered a broad answer to this, but let's see. The best recommendation that I would say would have to be to choose a field that you enjoy studying and working in. I know a lot of times, and I'm also present on some other servers and engineering student servers, and a lot of times people will choose a field because they think they'll make the most money in that field. A lot of times that has to do with computer science or something like that, or software development, or a lot of these fields that are kind of growing a lot more now. And I think that's a big mistake that people make. Um, yes, it's important to make money when when you're trying to support yourself, potentially a family. Um, and of course, you might not want to pick, a direction that's not going to lead to a maybe a comfortable, I guess I should say, paycheck, especially if you're going to university. I mean, it's rather expensive, especially in the United States. Um, and but I see a lot of people make the mistake that they choose a very specific field because that's, they don't know too much about it. Um, and I'd say that, go with something that you think is interesting to you, that you'll enjoy doing. Um, and if that means that you have to change, your major after the first year or two, if you decide you want to do something and then you don't quite like it, and you want to go in a different direction. I mean, that's totally fine, and that's perfectly acceptable to do, especially if it's going to lead to a more fulfilling career, because um, it eventually leads to your mental state and your mental health, and that's a very important thing that a lot of people sort of neglect when they're making these decisions. And so that's something that I'd say is, do something that you'll eventually enjoy. Um, Another mistake that people make, they think that if they choose something that they enjoy, that they won't ever have to really work. I think there's a saying, if you get a job doing what you love, you won't work a day in your life, and that's also incorrect. A job is a job. Your career, you still have to work a job, and it's going to be tough work, especially in engineering. But there's going to be a lot of days where you're going to enjoy doing it, but there will also be days that you might not enjoy doing it, and that's depending on maybe a specific project, specific person you're working with, like a customer, client, or something like that, and they might make things a little bit more difficult, and just kind of if you get through it, that should help. Um, so I think that's kind of a long answer, but just the simple go with your passions, I think, and that's kind of important. Um, so I hope I've answered that question. I don't know if anyone has a follow up to that. That's fine too. Um,
I think that was a good answer. And it was a bit of a broad question, but uh,
mhm.
I like I liked your answer at least. Mustang Steve asks on slide 6, based on a quick glance of people who have taken the coterm option, do you observe a financial advantage for people that graduate with a master's?
That is a good question. I'd say probably anecdotally, yes. And the reason for that being that with a master's, a lot of times you have the ability to take or to apply for different types of jobs. So in my field, in structural engineering, a lot of times they will require a master's degree, even for an entry level structural engineering position. And that's just because the type of work that you're doing is kind of a complex level, and just the general bachelor's in civil engineering, even with a structural specialization, doesn't really help all that much. There's a lot of things that you do need to learn above what the general bachelor's education will offer. And so in that term, yes, there could be a financial advantage in the sense that you have the opportunity for a higher paying job. Um, in terms of the pay for the school, um, I didn't really see much of a difference myself. A lot of the like the scholarships or grants that I had, they just kind of carry over because you're still an undergraduate student. Most of the time, there's really not very many scholarships or financial help besides loans for grad school. And so, doing an extra year with your undergraduate status will help with that as well. Although, depending on what types of grant you have, if you end up with some sort of student assistance for paying, they do have time limits on them, or rather, I should say, like a certain amount of semesters that they'll pay for, and so some of those might end up drying up as well. But there is available assistance for grad students as well. So I hope I kind of answered that. I wasn't quite sure which direction that they were looking at in terms of like paying for school or for having a higher pay at the end. So I kind of answered both of those. um,
Awesome. No, thank you. Mustang Steve had another question for you. They ask, when you applied for your PhD program, did you need a PI to agree on a topic slash research plan prior to fellowship application? How detailed does the scope need to be?
Yeah, so the answer to that is yes. So when I applied for the fellowship, I was applying specifically with a project in mind, uh, studying under a specific professor at a specific university. And so all of these things are factors in the fellowship application. Now, there is leeway in if you decide to leave or go to a different university, there's a way to apply to have that transfer. Um, a lot of times, I don't think that really happens all that often. Most of the time, if you end up not wanting to do it, you'll just drop out and then the fellowship just kind of goes away. But yeah, I did need to have um, a PI lined up with the project to be my advisor, and so his name was actually on the application as well. And um, every year, actually, we had to do an annual review where I had to kind of give them an update. It was a very brief update and just kind of like a paragraph of what I worked on, what I want to work on next semester or next year, I guess. Yeah, it was a yearly thing. In terms of developing my PhD research, and he actually had to go into the system and approve it as well. Um, and then the second, how detailed does the scope need to be? I mean, we wrote like a 2 or 3 page or 2 page proposal, I think. So I mean, it needed to be pretty well detailed in terms of the overview of what we wanted to do. We did give a little bit of specifics on how we might accomplish it, but they're not really as interested, I think, in the specifics. Or I mean, they're interested, but they're not expecting you to have the entire project, lined up ahead of time. Just the kind of the main idea. They in this sort of fellowship application, they had like a whole scope for the Office of Nuclear Energy is trying to promote nuclear energy going forward in the future, and how can we advance this direction. So there's a number of different ways to do that, and of course ours was this uncertainty analysis to kind of give an enhancement to the reliability estimation for these systems. And so if you have a more reliable system, you have a safer system, and you can kind of go from there. So I mean, it was pretty detailed, but there were a lot of changes that we made along the way, and that's perfectly acceptable, and probably expected as well. So
Great. And then we have one more from Mustang Steve. I promise there are others. Does A&L get funded by the DOE? Have there been layoffs or project shifts as political spectrum swings? And if so, how does A&L prep for that? Or does the engineering services division work differently? And if you need me to repeat any of that later, I can.
okay. Well, I have it open on my phone here too, just so that I can kind of get I can kind of go back to the text there. But let's see. So the first answer, does ANL get funded by the DOE? And the answer to that is yes. I don't know exactly the exact proportion, but I will say at the very least 90% of our funding comes from the DOE. Some projects, depending on which field you're working in, we have a lot of different divisions at ANL, and so some of them might be working on projects which get funded by a different, um, like perhaps the Department of Defense. I'm not entirely sure about that though, because I don't really work with any of those. But yeah, I mean, majority of the funding comes from DOE. As far as layoffs or project shifts, I haven't really seen any of that myself. Our division does work a little bit differently. A lot of the stuff that we work on still does come from the DOE in terms of funding. So we will get like we reach out to customers who have a need for engineering services, and a lot of times that comes from previous relationships of like other people who work in the department. Our manager brings in a ton of work for us, of course, but we are also expected individually to kind of secure some funding for ourselves as well, especially if we're running out of project money to fund our own work. Um, And yeah, I mean, as far as I've seen, I mean, we haven't really been affected by any of that. I mean, I know even with this, past year and a half of COVID, I mean, our hiring process hasn't slowed down at all. I mean, they hired a bunch of people still last year, and our growth is, it's continuing. Um, I mean, I can see how some political things might affect it. I know recently a lot of stuff has actually been, um, positive in terms of funding. So I know that some stuff has just been passed that has increased some DOE funding for a bunch of different projects. Now, whether those actually do get funded or not is based on, budgetary, and committees and stuff like that. So it's still a process, and we are affected by, continuing resolutions for the budget impasses and stuff. A lot of times it doesn't necessarily stop our funding, but it will kind of push it back a little bit. And so we do kind of have to wait on a couple of things sometimes. Um, so yeah, and then other divisions do work a lot differently depending on the type of work that they're doing. They might be directly funded by, the DOE, like through a specific fund that they're working on a research thing. I mean, most of our work in the engineering services isn't research based. So it's service based, and so our one of our customers will have money from DOE for something, and then they'll pay us to do it for them. Um, as opposed to if they tried to hire someone outside of A&L to do it, it would be more expensive. Um, so, and I mean, and not just the expense, but our expertise is very broad, so we can take on a number of projects. So that hopefully that answers the question. If there's anything else, feel free to ask more. I can always answer more on that if there's anything that wasn't clear.
Yeah, follow-up questions are accepted as well. But I think you explained it pretty well. Thank you. And then Step on the Tigress asks, do you have an EI or PE, an engineering and training or professional engineering license?
Ah, yeah, yes. So I do have the EI. It depends on the state what they call it. I know a lot of places call them EIT, engineering and training. Sometimes EI, engineering or engineer intern. I think Illinois calls them professional engineer intern. I do have that. Yeah, I guess I didn't mention that. I don't actually have the PE yet. So a lot of people might know this, but to get the PE requires 4 years of experience in order to get the license. In most states, especially Illinois, you can take it immediately after getting your EI, the exam. I mean, um, now one of the differences in Illinois, California, I think a couple other states, maybe there might be four. We actually have differences between structural engineering and professional engineer. And so, structural engineer, in order to sign off on structural specific applications, you need an SE license. Um, and so that has different requirements than the PE. And it requires a different exam to be taken. And for that license specifically, you actually need 4 years of experience to even take the exam. So, as opposed to the PE, where you can take the PE kind of right away after you graduate, for the SE, you cannot. And so, my plan of action was to go for the SE license, since I prefer, structural specific applications. Um, and so, I'm kind of in the process of figuring out the best way to go about doing that now. I actually talked to my manager a couple weeks ago about, you know, if there was funding available for, taking some classes, like the prep classes, or, buying some resources that we could use in the group that I can then borrow and take to the exam. Because it's, as far as I know, it's still going to be an open book paper exam. You bring your materials with you. I know the PE is supposed to be changing in some manner to a computer based exam, but yeah. So my eventual path was to go for the SE instead, and so I've been waiting on that because I kind of need to generate more experience. Grad school usually does account for 1 year, and I believe I believe the way that it works in Illinois is grad school, the degree itself can apply for one, and then PhD can apply for one more year. So I might actually have enough experience now to go for it. So my plan is to do that. The difference between the exams, the SE exam is actually 2 days instead of one. So it's a much more complicated exam that focuses on a bunch of different things. So I hope that answers that question.
I think it does, and I personally hadn't heard about the SE exam before, so that's an interesting new topic to hear about. See, Step on the Tigress also asked for the cracked walls slash bricks. How did you recommend to fix it? Wouldn't that be a geotechnical slash settlement issue?
Yeah. So that's. I mean, that is a good point. I mean, considering it was only a school project, it's a little bit different type of. A lot of times, the examination, if it's a more complicated examination, the general suggested fix is to have someone do a more in-depth inspection to figure out why it's happening. Now, when we're talking about cracks on the walls like that, depending on where the crack is happening and what direction the crack is happening, so a diagonal crack would most likely be a settlement foundation issue. For vertical cracks that actually happen in between, or rather not in between. So like the diagonal cracks will happen usually in between the bricks. So in the mortar itself, will start to pull away. When you have vertical cracks that happen even in that cut right through the brick, even that's most likely, not all the time, most likely based on excessive loading at the top level. So in our case, I don't think that was happening, but in some cases, you might have maybe your air conditioning system or something is too heavy for the type of uh, you know uh, wall that it's kind of sitting on. If the wall itself is not meant to bear that type of load, most of the time, sort of, we'll call them brick veneer walls. They're mainly designed to support their own weight, and that's kind of it. They're not really meant to support the load of anything else on top of them. So if they're if anything is exceeding that limit, you can get a vertical crack happening. Um, so in that case, the suggested fix would be to take whatever is causing that and to move it to a different location, redesign it, or perhaps design some sort of a supporting structure to offset some of that loading. In our case, I believe a lot of it was mostly, some other type of fix would need to happen. They would need to look at inspecting, the foundation and perhaps doing some sort of fix to that. There are ways to actually lift, depending on the type of foundation system you have. There are ways to. They have this. I don't quite know if it's like a hard foam type where they can inject it underneath the foundation to lift it up and sort of um, fix any sort of differential settlement that you have. In this case, that's something that might be considered for that building. One of the main issues with that building specifically is that if I remember correctly, it's listed as a National Historic Landmark because it's designed by Mies van der Rohe. And so there's not a lot that you can actually do to the building without either changing its status on the registry, or you'd have to preserve the entire outside of the building in order to do it. And so there's a lot of work then, and that ends up costing a lot more money to fix something like that when you have to sort of maintain the original look. I mean, you can obviously repair things and restore them to the original status or the original like look, but you can't actually make actual changes to the architecture. So yeah, it is complicated. A lot of the fixes were mostly based on the windows, though. So I mean, in that case, it's we just need to replace all the windows, and that of course itself is very expensive. And then just cleaning up and repainting the exposed steel on the outside, which, believe it or not, some of that exposed steel could have also been causing some of the cracks. a lot of things that are sometimes people don't know this, but when steel and metal actually rust, the corrosion actually increases the volume because it's adding new material on top of it, and that sort of excess stress can actually cause, the window frames to bend and can actually cause extra stress on the wall itself. So, I mean, that's something that they could have also done. I believe they did actually repaint the steel, so, or at least on one part of the building. I don't know if they did the whole thing. Um, so,
All right. Stepan Tigris also asked, does your plant require their own water system?
um, so I'm not quite sure what in terms of like nuclear power plants. So one of the I guess is not very clear from my presentation is that a lot of the work that I do is on at the research level. We're dealing with academic or research based nuclear reactors, so we're not actually dealing with an existing nuclear reactor. So I'm not quite sure if that's what the question is asking for or asking about. So I don't actually work on any specific like nuclear power plant or anything like that. Um, Now, in a general sense, if you're talking about like just in like a general nuclear power plant, I mean, yeah, that would probably be required. I know a lot of times thermal power stations are built around water for that specific reason, around existing water structure, like water systems. Um, so but that's kind of out of the scope of where my research is. My work is mostly focused on the internal side. So you would have to probably ask someone who works on either designing or maintaining like nuclear power plants in general.
All right. Well, they do say that's good for an answer. So
Okay,
that
that's good.
um, Mustang Steve asks, can you share the course number for seismic design? Is it open for all, or was this course created as an action to Fukushima?
Oh, yeah. So the seismic course that I took was just a general earthquake engineering course. It wasn't specific to nuclear power plants. I mean, in fact, it was mostly focused on just general buildings. The for IIT's course number is CAE 586. I mean, I guess it's technically open. I mean, it was um, it was just the general educational course. So I mean, if you're structural engineering student and you wanted to take that course, I mean, you definitely could. Um, I'm not. Uh, yeah, I mean, you'd have to be a student. I'm sure, but yeah, I mean, it was just a general seismic engineering course.
All right. And then on slide 8, it seems you mentioned an honor society. Did you benefit from being in that honor society? Or do you feel like you currently have any benefits from that?
That's a good question. The short answer is probably not. And I know that probably sounds a little bit scary. Um, Generally, when you're a student in an honor society, you benefit more depending on the specific university that you're at and how active that chapter is. And so, I mean, when I was in the honor society, I actually was the president of the honor society, and it was the year that we had our national conclave, where we all of the chapters in the country met we met in Texas, and so we did have specific meetings, and we talked about like what groups do and what other things that we can do. And so I mean, if your chapter is more active and they want to provide I know a lot of times we were talking about like providing assistance for PE exam instructions that like we can have like grad students actually give some lectures or courses on or I should say more like review courses on specific like structural engineering applications that might appear. Currently, I don't have like a student-based um, honor society. If I were more active and like maybe active with like the national chapter, perhaps, but it is geared more towards students, I'd say, which is probably one of the biggest like downsides of that. It's like it really depends on how active like the local chapters are. Obviously, some other like student organizations, especially for civil, like ASCE, would be a little bit more probably. You'd get a lot more out of it because they're at least at my university they were way more active. But I know at some other universities even that chapter might not be as active, and it really depends. But personally, I mean, yeah, I don't really get that much out of it right now. So and especially since most of my focus has been changed. Most of the work I do is actually mechanical now, so it's I should probably get involved with ASME instead. So yeah, or NSE, or sorry, not NSE, ANS, the nuclear um, the nuclear one.
Yep, fair enough. Let's see. Mustang Steve also asking, the world seems undecided on nuclear, even though carbon neutrality is being shoved into the spotlight. Care to comment on how this conversation has played out in the hallways of A&L?
Um, I, was this, green energy that, and the nuclear kind of gets shoved off to the side, and that's a nuclear reactor, and the cost is money and time, and a lot of that is due to the regulations, and that's we don't want to have you know the issues that, and so there's a lot of regulation that goes into designing and building. A lot of people don't know how they work. They um, a bunch of people talk about, but then one of the other aspects you're not really sure about, and a lot of times a lot of, I don't want to necessarily say false, but a lot of incorrect statements are made, and it can scare people because of things like Chernobyl, and that is completely different. Completely different situation than what is the case in the United States, and even other countries. Um, Now, the other thing is, a lot of the reactors that were doing this that are LFRs, not L, I'm sorry, completely different than a sodium-cooled fast reactor because it uses water to cool it instead. And then another large portion of those are pressurized water reactors. And they're in the system. I know a lot of companies actually work on doing stuff like that. A lot of technology, and anytime you get like a new type of technology, I mean, 60, a lot of work that's been done on this, but it um like how the conversation. So I've actually really only been on site in my current position the last couple months, only a couple times couple days a week. Is the nuclear science and engineering division, and so their entire push is to push nuclear engineering, and nuclear power as a viable energy source for the United States and in the future. Um, and we do get quite a bit of you know research money to fund all of this stuff. So I mean, there's a very positive outlook on it, but a lot of the work at A&L also focuses on different types of technology, like batteries and um, I mean other types of renewable energies as well. So I mean, there's we like to cover a wide variety of things because that's kind of what everyone's really looking for, is not just one sort of solution to fix a lot of the issues that we have. Um, but I'd say, it's in terms of nuclear is very positive around A&L, considering the history. People might not know is actually, where the first nuclear reactor was developed. Or I should say, the first nuclear chain reaction, which is the mechanism for actually starting a nuclear reactor, was actually started because of the work done at A&L. So um, yeah, I don't know. I mean, it'll be interesting to see how that continues going forward. I mean, my hope is that it does continue. Maybe I have a bit of bias in that sense. I mean, but yeah, so it's an interesting topic to say the least, I guess. But yeah.
Okay. And kind of building off of that, D767 asks, what do you think of thorium reactors? I don't know.
That is a good question. I As far as I know, I mean, I've heard that they're doing some really good stuff with that. I'm not really exposed that much to it myself, so I don't actually have a lot of the specifics. So I don't really have that much of an opinion on them. But it's definitely something that I probably should look into a little bit more just to kind of see. But yeah, I mean, my work is a little bit more. It's focused in a different area than that. So
Yeah, fair enough. I mean, one of the best answers you can give in engineering, I think, is yeah, I don't know, but I'll get back to you.
yeah, exactly.
I think that's fair. Um, I'd like to ask you, what's kind of digging into your experience a little bit. Have you had a particularly interesting problem at work, or a difficult challenge that you've kind of overcome? I know it's been a brief time for you so far, but
Mhm.
uh, I think these are kind of fun questions. Do you have anything in mind?
Yes, actually. I will keep the specifics to a minimum on this one, but there is one of the projects that I'm working on, and it has actually been a very difficult time um, trying to get, I guess, sort of get exactly what the customer wants on it. So that's one of the things when you're working in engineering, is that client, customer, however you term, they're the ones who are paying for the work, or they're the ones who are using the results for something, and so you kind of have to go with what they say, even if you think it's not the right way to do it. Is the I guess the maybe the not political, but you know what I mean, like the nice way to say it. Um, and yeah, so this project that I'm working on with like a frame structure, and they're very insistent that we do this full 3D analysis, and it's a big headache because it's introducing so many complexities to the analysis that it's like, what, it takes way too long to do anything with it. And I believe that there's simplistic or more simplified ways that we can do the analysis, and so that's one of the challenges is you know, we do all this work and we write up a report and we send it to them, and then they get back to us with a million different questions and asking us why we didn't do this and this and this. And it's like, well, because it's maybe not necessary, or it's not really in the scope, or it's not really reliable to maybe rely on specific results that they're asking for. But it's something that you definitely have to consider when you're working, is that you know you you might think that you know what you're doing, and you have all these results and everything looks good, and you send it off to the customer and they review it and they say, well, we don't agree with you, or we want it done a different way, or we want more of this or that. And it's like, well, at that point you kind of have to do it, and realize that you're providing a service to someone else. And so it's not necessarily um, you know is- you're providing a service to someone else who is not necessarily an engineer and might not know the types of um, like the specific ways that something should be done, because they don't have that sort of expertise. They don't have the design expertise. They might have enough knowledge to understand what's happening, but obviously they rely on you to do the work for them. And so you kind of have to sometimes swallow your pride a little bit and say, okay, well, we'll just do we'll do a little bit more in this, and you know try to do it in a way that makes them happy, while also minimizing as much of the burden on the how hard or difficult everything is to actually get it to work. And so that's one of the things that I'm kind of struggling with right now, is you can do all of the analysis you want, but sometimes it's just not either enough, or it's not uh it's not presented in the way that they want it. And so you kind of have to go back and redo a bunch of things, or change a couple things. And so that's one of the things that I'm kind of working with. And one of the, I mean, it's a larger project, and someone else who's working on a different part of it just calls it the never ending project. And I kind of say that as well, or like the project that never ends, because it's always they always come back to us with something after we give them results, and they're just like, well, why didn't you do this or this? And it's like, well, okay, we'll do that then. So
Yeah, I've been in a similar position. I know what you mean. But yeah, some office politics, or public relations, customer relations, maybe.
yeah, exactly.
Okay. Well, let me ask you real quick if there are any follow up questions. Of course, anyone is welcome to post them in the thread for the next 24 hours after the most recent submission until it is archived. Um, and we'll try and pass those along to Dr. Yin as well. Um, but would you be okay with people directly messaging you if they have any other questions as well?
Yeah, that would be fine. I try to be as available as possible on Discord. I mean, I do work, so I have a large portion of the day that I'm not really that available. Um, I mean, I will say, if they're kind of limited to like questions about stuff like this, that would be better. I'm on another server, and sometimes I'll get questions about like homework related stuff, and I'm not. I mean, I help out on the server as much as possible, but I try not to help out in direct messages for stuff like that. But if it's related to this type of work, or just general questions or something, yeah, that would be fine.
Sure, I think that's very reasonable, and generous of you to accept those kind of messages, regardless. We do have one more question for you. Wheat asks, either during your fellowship or now working for engineering services, was there a requirement or concerted effort to learn the nuclear physics side of things, or were you left to pick it up as you went along?
That yeah. So I was kind of I guess the way to say this, I was kind of left to kind of pick that up on my own. And I guess the way that I'll say, I approached it in a way where I learned as little as possible to understand how things happen. So that way I wasn't trying to learn an entire new field, which would be its own sort of degree, on its own. But I learned enough to kind of understand how those physics affect the reactor in the way that it does. Um, because that's important to doing the analysis. Um, Most of the analysis, I guess I can say a lot of software that were originally developed for doing nuclear reactor analysis, they're all decoupled, so they can solve the physics individually and kind of pass things back and forth. And so a lot of it's specific software might be developed to doing just the structural component. So as long as you have the inputs, you can do the analysis without really needing to know a lot of the other physics. But to actually discuss it with other people, you do need to know enough to actually understand what they're talking about. And so I'd say that I kind of picked that up while I was doing my research. So the big portion of the doing any sort of large research project is doing a literature review, and so you kind of have to go and look at previous work that's been done, and a lot of them will talk about a lot of the physics phenomena that's happening, and that's sort of how you pick it up based on what they're talking about, and then you kind of go through and look up more on that so that you can reinforce the knowledge yourself. And that's kind of what I did. There was no um, like effort to kind of teach that to me. My advisor himself didn't even really know it. I was kind of teaching him while I was doing the PhD process. We have our meetings, and I kind of discuss my literature review, and I'm kind of giving him the information on that part of it. So, yeah, it was. It was a little bit different. Most of the time, you might not have to do that in a PhD. You might have to learn enough about another topic, but maybe not that much because you're kind of focused in on that area already. But since I didn't have a nuclear background going into it, I kind of had to, do a little bit extra work, I think, and kind of pick that up myself.
Wonderful. Yeah, I think that makes sense, and especially if you have knowledgeable coworkers, people who really enjoy their jobs, I believe tend to love talking about it and love talking about their work. So if you're around them, it's not hard to imagine you pick up some of that.
Yeah. Oh, and I will say on that, yeah, especially at work. I mean, a lot of the uh, I guess one of the projects specifically that I'm on, we do have regular meetings where I discuss my work and other people discuss theirs as well, and so you do pick up stuff like that as well. And um, specifically at Argonne, you're pretty much everyone I talk to, and everyone always says feel free to ask any questions you have. Everyone is extremely open to helping with anything that you have, as long as it doesn't take away from their own work, obviously. But everyone's pretty open to answering questions or helping out. And so there's always that, if you're not sure about something, just ask. And I know a lot of other workplaces have that sort of feel as well. And so you should always feel free to ask questions of, whenever you're not certain of something. And then for these, projects, they're usually part of larger projects. So it's like a small subsection. And so, uh, especially for these DOE projects, every year we'll have like annual reviews where the project leads for every single task will go through and sort of very, very briefly at like the highest level possible give like one or two slides on like some of the work that's being done. And so you do pick up stuff like that as well, like figure out like who's doing what sort of work and how everything kind of fits together.
Yeah, yeah, those kinds of meetings I think can be very informative as well, um, especially for the particular project, or at least in that context. But I don't see any more questions. Again, if there are any other questions, you can put them in the Q&A thread, and we'll try and pass those along, or you can direct message Dr. Yin directly, and as long as it's appropriate, it sounds like he's willing to get back to you at a reasonable time. I want to thank you again, Dr. Yin, for your time. You've been very generous with it, and I want to thank everyone who's joined us tonight. Uh, y'all have been very patient, and though you were all muted, you've been a wonderful audience. And I appreciate all the questions that y'all have asked tonight. Y'all have helped keep the discussion lively. Um, we do have one straggler question I want to ask. Do you know much about getting into this industry outside of the US?
Um, the short answer is no. It's yeah, because I mean, I'm not really sure how the industry is really uh like how it's handled outside of the U.S. I mean, I know in our case, I mean, I didn't really have to do very much in particular besides just working and having some working relationships with people. Um, and with me being a U.S. citizen, of course, that also is reduced the number of barriers as well. But I mean, depending on where you're from, I mean, I would just try to look around, see if there are research opportunities. They don't have to be super high level research. You know, uh, see what's available. Depending on what university you go to, maybe look at some programs that exist. Uh, you know, your best bet for actually getting into any sort of industry is to be involved with the program and sort of communicate with people or organizations, and so that you have access to the people who work in the industry. And once you have access to the people who work in any industry, you have that sort of potential pathway into the industry. So that's probably something that I would recommend, is just to kind of get involved as much as possible. Look things up to see potential job openings, depending on where you are in your school, or if you're already graduated. Um, that probably makes it a little bit more difficult if you're already graduated, just because depending on your background, you might not have the necessary experience or education. But there's always a way through to something. So I mean, in my case, civil um, is not specifically nuclear engineering, and so even I was able to get into it. So I mean, just kind of look around, talk to people, get involved with things. That's always the best answer. Um, and then just you'd have to just go from there and see what happens.
Wonderful. I think that's a great response that's applicable to really everyone. So thank you for that. And again, one last time, thank you for your time and thank you for everyone else who's attended tonight. Again, this video will be posted on our YouTube channel, and when that happens, we will make an announcement in our announcements channel here on the Discord. Um, Again, if y'all are entertained by this, if you've learned anything, please tell your friends, share the video that will be posted. If y'all have any follow up questions, you can ask them and we'll get those answered. If you are interested in our Resumania events where we do live resume reviews, please note that we will be skipping next week due to the holidays, but we will be doing another event in 2 weeks on December 3rd. And you'll learn more about that in the announcements channel or by asking us. That's really all for tonight. Thank you all, and I think we can end the recording here.